This video details the modal acoustic emission examination of a Type 4 composite pressure cylinder in accordance with ISO draft standard 19016 and the already accepted NBIC NB10-0601 code. This particular cylinder has been highlighted as the response of the cylinder was quite anomalous. The MAE examination was requested due to the composite pressure cylinder being involved in a motor vehicle accident where the composite may have experienced damage. As the cylinder had a higher than usual probability of having compromised structural integrity, pressurization method A of ISO 19016 was selected by the Level 3 overseeing the program. By utilizing the test pressure of the composite cylinder, the structural integrity could be more thoroughly investigated. The cylinder has a nominal 1 meter diameter and a 10 meter length. The service pressure of the cylinder is 3,625 psi, which resulted in a test pressure of 5,492 psi. Given the considerable size of this composite pressure cylinder, it will become quite clear that the modal acoustic emission technique scales from exceptionally small to the largest composite pressure cylinders in the world. Due to the size of the cylinder, a total of 54 channels were used. Prior to testing the cylinder, an attenuation study was performed to show that the high-frequency component of waveforms could propagate sufficient distance in specific directions without attenuating below the noise floor using the particular broadband transducers that were to be employed during the pressurization of the cylinder. The attenuation analysis was presented to the independent authority, the method accepted, and the increased sensor spacing was used. In this sensor placement diagram, it can be seen that a total of 54 channels were used, 3 on each hoop bands, with a total of 18 individual hoop bands. It is also seen that transducers are rotated 60 degrees on respective hoop bands to ensure maximum coverage. In this video, we will concentrate our efforts on the waveform detection, examination, and the subsequent evaluation of the 3 acceptance criteria of ISO 19016. The plot on the left-hand side of the screen is a double Y plot where the left-hand Y-axis is the background energy of the respective waveforms. The right-hand Y-axis is the hydrostatic pressure being applied to the cylinder, and the X-axis is the total time in the current test. Note, in the left-hand plot, channels 13 through 15 are denoted by their respective symbol, and the pressure within the cylinder is indicated by a solid blue line. The plots on the right-hand side of the screen correspond to 3 oscilloscope windows showing the detected waveforms on channels 13 through 15. Channel 13 is the top waveform plot, channel 14 is the middle waveform plot, and channel 15 is the bottom waveform plot. In this analysis, we are focusing our efforts on channels 13 through 15 due to post-test finding that these channels were the most interesting. Channels 13 through 15 were also the most interesting because pre-test a visual indication was found on the composite cylinder as a result of the motor vehicle incident. The visual indication was not significant enough to fail the cylinder on external visual inspection by either CGA C62 or the special permit visual inspection criteria. The placement of transducer for channel 14 was located approximately 12 inches in the hoop direction from pre-test visual indication. Based upon prior testing of this composite pressure cylinder construction and finite element damage mechanics computations, the Level 3 overseeing the program determined that the fiber toe fracture energy was to be 2.7 e to the minus 15 joules. Similarly, the single event energy was established as 2.7 e to the minus 13 joules. The background energy rise and oscillation parameters, M1 and M2 in ISO 19016, were both set at a factor of 2. Getting into the actual pressurization of the cylinder, it is seen that there is a quiet background energy. Damage mechanisms are being detected but the background energy level, particularly on channel 14, is remaining relatively stable and flat. This value can be taken as the quiescent level of the background energy for channel 14. It is seen around 710 seconds, a small rise in the background energy is observed. However, this rise in the background energy did not exceed the allowable value. With the pressure still increasing, around 735 seconds, we see a violation of the background energy rise and oscillation parameters on channel 14, with the excursion going from 0.004 volt squared microseconds up past 0.01 volt squared microseconds. Such an occurrence is particularly interesting and unusual due to the fact that this occurred at the service pressure of the cylinder. This is highly indicative that something is significantly wrong with the composite material. On this particular test, we had to go into an unscheduled hold due to the reservoir for the hydrostatic pump running too low. During this lack of increasing pressure, we have sped up the playback of the test for brevity. Interestingly, however, it is noted that several damage mechanisms are still being detected on channel 14 in the absence of an increasing stress state within the composite laminate. This is particularly concerning given that such an occurrence is not normally observed. With the reservoir filled and pressure once again increasing, several background energy oscillations and partial fiber toe fractures are noted at 4,000, 4,300, and 4,800 psi, all occurring on channel 14. The background energy oscillations are a direct result of the onset of local instability in this volume of the composite cylinder. This local instability is caused by the statistical nature in which the composite materials fail, and is generally referred to as the weakest link theory. As a volume of the composite fails, the stress that volume of material was carrying is transferred to neighboring undamaged material through shear lag of the epoxy resin. If the neighboring material is too weak to carry the new increased load, it too fails, resulting in a multitude of damage mechanisms occurring near simultaneously, and a rise in the background energy. Eventually, load is shed to a strong enough part of the microstructure that the composite stabilizes and the background energy level drops. As pressure increases and the state of stress within the laminate increases, additional weak material fails and the process may repeat itself. Moreover, frequency and mode shape analysis of the detected waveforms on the first pressurization of this cylinder indicated that 132 fiber fracture events were detected during the first pressurization on channels 13 through 15. 125 of these events occurred nearest channel 14. A source location analysis was performed and indicated that 101 of the detected fiber fracture events located back to within an inch of the pretest damage indication. The largest of the fiber toe fracture events was approximately 1.5 fiber toes failing simultaneously from an energy analysis. Post-test, visual observations confirm that several hoop fiber bands had fractured. Transient dynamic finite element simulations were used to confirm that several of the fiber toe fracture events were hoop wraps. Post-test visual confirmation of the hoop toe fiber fractures lends credence to the forward predictive capability that makes MAE such an attractive non-destructive evaluation technique. Into the test pressure hold, a few sporadic events occur, but the background energy level at the current stress state has stabilized and the cylinder is not progressing to failure. To complete pressurization method A second test pressure cycle was applied to the cylinder. In the interest of brevity, the second test pressure cycle is not included in this video. Post-test analysis of the detected waveforms found that the fiber toe fracture energy, single event energy, and background energy oscillation rise were violated, causing the cylinder to be condemned in the absence of any repair work.